All right, let's get started. All right, good afternoon. Welcome everybody to this talk about log indexing with Apache Flume and Solr Cloud. It's going to be a lot of material, so I'm going to race through a few slides, and hopefully there's going to be time for questions at the end. So the agenda is a brief intro about who we are, what we do, and why do we use Solr and Flume, what kind of problem we are going to solve, and how does Solr and Flume help with our particular problem. There's going to be an example about syslog, like how do we index this, like how do we parse it, and some examples about HA, DR, and scalability. First, about me, I'm Ops Architect at Cisco CCATG, better known as WebEx. My job is to ensure operational readiness for complex distributed services that we provide. And that what it really means is HA, DR, configuration, deployment, and things like that. Previously, I spent 8 years at eBay, Excite, IBM, and Visa, doing similar kind of operations architecture and monitoring and event correlation. So by now, you probably wonder, like, why do I speak in a funny way? And the reason is that I come from northern Finland in a town called Kemi. And in Kemi, last week, the sun did not set at all. So you can see it's pretty, daylight is 24 hours. No night at all. So it's kind of fun place in the summer, but the winter is opposite. It's night all the time. So Cisco CCATG is Cloud Collaboration Application Technology Group. It's a bit of a mouthful. So what we do is WebEx meetings. Is there anybody in a room who doesn't know who WebEx meeting is? Somebody who hasn't used a WebEx meeting? Show hands. One. That's great. WebEx is pretty widely known and widely used. The other things we do is Cisco WebEx meeting messenger, which is basically IM, Jabber-based technology, IM presence, and Cisco WebEx social, which is social networking for corporations. But by far, WebEx is the biggest chunk of the business. So this BU is about a $1 billion business unit, so it's pretty big, although in Cisco world it's fairly small. So WebEx is it was the first software as a service at scale. So like 10 years ago, Salesforce used to say that we are like WebEx, and now the roles are a little bit changed. So, but we are still number 2 as a software as a service provider. So we run our own cloud. We have data centers in more than 10 locations around the globe, different regions. Some of the data centers are big, like thousands of servers, some are small, just like a point of presence to get the traffic in. And we operate our own network. So we have leased circuits between the data centers, like 10 gigs. And I sit next to the person who provisions statistics, and she goes even that far that she checks that where are they actually provisioned, because we buy circuits from different vendors. So if they're in the same physical location, that doesn't really help, because there are occasions when cables are cut, and if they're all cut at the same time, it doesn't matter if you bought them from different vendors. So the service is multi-tenant. There's 95,000 sites provisioned, and it's really complex application. There's website, there's voice, video, desktop sharing. So it's complicated to keep it running. So I'm in operation, and things break all the time. People make mistakes, hardware fails, software fails, even the failovers fail. So we have, everything is redundant, everything can fail over different data centers, but still there's outages. So what do we do with that? So there's this interesting concept from Berkeley called Recoveryoriented computing. So they say that some things are not just problems, they're just facts. Like if a problem has no solution, it's not a problem, it's a fact that you need to deal with. So what it means in our world is that people, hardware, software failures are facts. They just, we can't get rid of them, like they just happen. So we have to deal with them. And the way you deal with them is that, so our job is to provide high availability. That's our main charter. And the way you deliver high availability is to recover fast. So basically we need to decrease the mean time to recover. So that's where they get the biggest bang for the buck. With the mean time between failure is harder to, it's usually much bigger, so it's easier to get better availability by reducing the mean time to recover. So this is kind of lead up for how do we make, like why do we use Solr and Flume to index logs. So I sold this idea to my boss when I came to Cisco that we should build this kind of system that we can recover fast and find problems. Basically, like what is the root cause for outage? So then I went even further and said, okay, we need to be proactive. We need to predict when things break. So I built a system and I put the query in the system and hit enter, and I didn't get lucky. I actually tried this for fun, but that's the response that comes out of it. So aiming to a lower call, which is just, it's not just, but it's near real-time full-text search, and I'll get to, so this is the end goal. Basically index logs and find them easily and find what's going on with the system. So let's move on to the system that we have. So this is an overview of the log collection system. So we have logs coming out of various places, like mainly applications write logs to local disk, because all these systems were built a long time ago. So they don't make any RPC calls or anything like that right now. So we have to pick them up from local disks or syslog. We can also use Drift or Avro from now on when we build new systems. So from there, the flow goes to Flume and to HDFS, and it's fan out to Solr Sync to Solr Cloud. And we can also do other real-time correlation using the same flow. So it's basically, you can see the Flume in a way like a pub subsystem. So there's a fire hose of events coming in, and you can fork it out to different destinations like long-term storage in HDFS and indexing with Solr Sync. And the structured data comes from RDBMS with the scoop. Sometimes you need to do joins with transactional data and log data, so we need to move that as well. And there's an application that controls the access to Flume. So there's an access token that we generate so that only certain service can send events via Flume. So this is an addition to customization for the system. Because we are Cisco, of course we use Cisco hardware. Cisco uses C240s with 12 times 3 terabyte disk, and this gives effective storage of 9 terabytes usable after three-way replication and temporary disk space, file space. So the next thing, let's drill into this Flume system. How is that configured? This is just like a logical overall view. So more details about this layer here. So the global Flume topology consists of collector tier that gets events in a local data center. Remember, we have like more than 10 data centers, and this collector tier is deployed to about 5 data centers where the main servers are. From there, it's streamed to storage tier that's in 2 data centers for redundancy. So each collector tier, Flume, streams data to 2 storage tier data centers, where it stores to HDFS and Solr Cloud. So then drilling deeper into the storage, into the collector tier. So this guy represents the single server in a collector tier. So it gets events from various sources through our source. And there's a fan out to 2 different channels that go to 2 different data centers. So if one data center goes down, the events are going to be buffered in the disk on the collector tier. There's more details about the failover later. But anyway, so this thing scales out by adding, you can scale out by adding channels in a server or adding these servers. So all events are fan out to 2 different data centers using the Solr using the Avro source. So then drilling deeper into the storage tier. Storage tier is similar to collector tier, but it gets the events from the higher level, which is the collector tier. And it multiplexes the events to HDFS for final storage and Solr sync using multiplexing fan-out system. So the multiplexing is kind of misleading. So it's not really multiplexing, but you can get all the events to HDFS and selected events to Solr sync using headers in events. So all events to HDFS and selected events to Flume using the headers. So this is kind of interesting topic, like schema or no schema, because Solr requires a schema. And so then you think, what the heck, like this is big data, there's no schema on write. But in Solr there's a schema on write, so why is that? And if you think about it, like when you deal with data, so there's always a schema somewhere. Like you can have the schema on read or schema on write, so it kind of depends what kind of flexibility and what kind of performance optimization you have. So with Solr, the reason why there is a schema on write is that it's really optimized for performance and functionality versus flexibility. For example, like if you don't parse the events into fields, then you can do faceting and by field different kind of functionality. So it's really about optimizations for storage and operations based on the field type. And that's kind of secret for Solr fast performance. So the takeaway is that there's, if you talk about schema and write or read, that there's always a schema somewhere. It's either in a central place or it's hidden in the application code. So I'm going to walk through a example of parsing a syslog stream of events. So this is done with Cloud removlines, which is a new feature in the most recent Flume release. So you can see this as a streaming ETL. So it's a framework to simplify the transformation of various events into something that's more suitable for Solr. And it's good for guys like me who are not Java programmers that, I don't need to know Java. I can just use the scripting language. And it's pretty easy to use. And even better, it's using existing grok patterns that if you are familiar with grok, it's a framework for having a library of regexes. So this is used with log stats, for example. So it leverages some existing frameworks that are already done. And it's also reusable with multiple workloads, so you can use it with Flume streaming or MapReduce jobs, the same way. So basically, the way it works, that the Flume event comes in, and Flume has headers and body. So what the morphline does, it's a pipeline of commands. So it takes a command, reads the line, converts it in some way, passes it to the next layer, and so on. And this pipeline at the end hits load Solr command, which implements the Solr API to load the record into Solr. So I walked through this whole thing in detail. So here's an example that probably everybody understands. So there's a simple syslog message coming from a Cisco ACE load balancer. So this is the way it looks like when it comes on a wire. So you could index this thing as one message, but it wouldn't be that easy to search, and you wouldn't be able to do any kind of faceting. So the end goal is to transform this one line into these fields. So there's basically, these are the fields that come out of syslog, the 5 fields, and these are the fields that are added by the morphline commands. So the first step is the read line. So after the read line, you got the Flume headers and the body in a record. So these are the headers that Flume syslog source added, and this is the body of the Flume event. So then the next step is to convert timestamp. When you index logs, the timestamp has to be, it's much easier, much better if it's in the same standard format like ISO 8601. And syslog timestamps are not in any kind of standard, but they're not really easily sortable, so you need to convert them. So there's a built-in command, convert timestamp in removlines, that does the job. Going forward, there's the command add values, so I can add or rename values. Like the field that came in from Flume was called category. So here with this command, I changed the field name to access token. So it's basically just renaming so that it matches the schema. Next step, this command called try rules. So with this command, I converted the severity 3 into label error. Like when you're in a console, it's much easier to sort things by labels rather than numbers. Like I don't remember this syslog severity is like what is 5 and what's 3 and so on. So it's much better that you label them. Again, try rules. So this basically passes the message part. So there's the message starting with the %ace. And there's some other fields that are parsed into smaller pieces like Cisco product, Cisco ID, and so on. So then you can sort and search by these fields later on. So going forward in the pipeline, there's a command called sanitize unknown Solr fields. So this command drops all the fields that doesn't match the schema. So basically when Flume starts, it contacts Zookeeper in the Solr Cloud and asks what are the fields that the schema has for this particular collection. So you have an option to also insert fields that don't match the schema, and they could be renamed with prefix something. So you don't have to drop them, but if you know what your flow, what your data is, then you can drop the things that you don't need. Next step is to generate UUID. So UUID is used by Solr for hashing the data across collections. So it's using murmur hash to kind of spread the data evenly. Like if you have like four shards, then the data is spread evenly across those 4 shards. And you need to have, this is the only required field that you need to have in a schema. And last command in the pipeline is Solr load. So this loads the events into Solr server. So again, here's the flow in summary. So Flume event comes in, header and body, and there's a series of commands that is transformed into a structure that matches the Solr schema. So brief intro about Solr Cloud. So Solr Cloud is a cluster of servers that has collections, shards, and replicas. So the collection is the index. So for example, if I index syslog, I would have a collection named syslog, and it's spread evenly across this cluster of, in this case, there are 6 servers, 3 shards. Each shard have a leader and a replica. And the file system can be pluggable. You can use local file system, or you can store the data in HDFS. Like in our case, we use the newly released Cloudera Search, which uses the HDFS as a file system. So we store the state, the indexed collection in HDFS. Zookeeper is the place where the state is kept for the cluster, and it also keeps the configuration and does the leader election for the shards. So this is fully HA. So if a server goes down, it's redundant. The client wouldn't see it. So if it comes back up, then it's synchronized with the leader. So it's in a recovery mode, and once it's recovered, it will turn into active and start serving queries. If the leader goes down, then the Zookeeper has to elect a new leader. And it elects a new leader, and the new leader starts accepting writes or adding documents. So this is all in near real time, which is a new feature in Solr, meaning that the newly inserted document is searchable within seconds. So you don't need to wait for a long time. Like in operation situation, if something happens, you want to search errors like within seconds. So here's a flow, like this is like Flume client here, and it asks the zookeeper where's the cluster. You can write to any node, and the node routes this request to the shard where it belongs, and the leader writes then the data to the replica. So this is a really high-level overview of Solr Cloud. There's a lot of stuff on the web, like you can Google like Mark Miller's Solr Cloud architecture. That's a good presentation about this, and you could spend the whole conference about talking about just Solr, so it's a big topic. I just kind of have a brief overview here. Here's the view how the Solr Cloud looks in the admin console. So basically, that's the collection of syslog, and it has 3 shards in this case, and replica and leader per shard. So Solr index management is the log indexing, a special corner case of indexing. So in logs, there's a lot of additions, and it's time series data. Everything has to be indexed by time. There's a very high indexing rate and very relatively low rate of searches. Like if you take like e-commerce situation, it's the reverse. Like there's not like thousands of new products coming per second, but there's thousands of queries coming per second. So this is the reverse of your usual use case. So you need to manage the collections by collection aliases, meaning that you rotate the collections by, for example, by day. So you always write the current day, and then when the next day comes, you rotate that out, and it ages out. And you basically expire the indices by dropping the old indices. So the next section in the talk is about Solr and HDFS DR. So Solr does not have any multi-data center support, neither does HDFS. But all our services run in multiple data centers, and they can survive data center failures. So we have to build in something in Solr and HDFS that can support data center failures, because our services does it already, so we can't be any worse than that. So how do you do it? So one option is this is probably the best option, is to use Flume for dual writes. So you got the collector there in multiple data centers, and the storage there in 2 data centers. And these 2 data centers both in the US, like in West Coast and East Coast. So collector there does dual writes to both data centers. And if data center goes down in this case I just put down the cluster. If it goes down for maintenance or planned or unplanned, then the collectors lose the connection and start streaming in a local Flume file channel. And once the data center comes, or the cluster comes back up, Flume collector tier reconnects and starts streaming and catching up. So at that point, these clusters are not up to date, and they actually don't know about the other cluster at all. There's no built-in support for Solr or HDFS about multi-data centers replication. So you need to build some kind of checking here that whether these clusters are in sync or not. So this scenario relies on Flume reliable delivery, which is Flume is built for that. But things happen, like things go out of sync, so you need to build some additional tools on top of Flume to make sure that the 2 clusters are in sync. And this way, it doesn't replicate any aggregate data. The other thing that we're going to explore is using disk copy and MapReduce. It's the same scenario. You got collector tier in multiple data centers and storage tier in 2 data centers. And in this case, the collector tier writes only to single data center. So this is kind of like active, passive, active standby scenario. So if this guy goes down, first here there's this copy of the detailed data to the other data center. So if this cluster goes down, the collector there starts buffering at the file channel layer. And you need to flip this traffic to the other side, for example, using using, or first you need to do MapReduce to index the data in a backup data center because it's not ready for the traffic yet. And then you need to flip the traffic using like CNAMEs and go the other way. When this guy comes back up, it's the opposite. Again, they are out of sync. You need to sync them up and flip the traffic again. So this is, it doesn't really work. So it's kind of complicated and the clusters are always out of sync. So we went with the replication with the Flume way. So next section is about scalability. So there are three tiers to scale: the collector tier, the storage tier, and the Solr Cloud. So first, the collector tier throughput. So this blob here represents the single data center where we have from 100 to thousands of servers. So we got some agents generating logs going to, this guy represents the single Flume server. So the first bottleneck there is the NIC. So we use single 1 gig interfaces. And so this limits the write rate for about 100 megabytes per second. The next thing is our source, which is not a bottleneck unless you do something with intersectors or channel selectors, because our source is customizable, so you can do your own code. So depending on what you do, you can degrade the performance at this layer. Next step is the file channel. So this is the bottleneck with the collector tier or with Flume in general, if you do reliable delivery. So in our testing, we got 14 megabytes per second throughput using one single file channel. And again, it's going to the next tier, which is the storage tier, and there's a NIC again. So 14 megs per Flume server. So when you get new clients coming online and you run out of capacity, you can scale out by adding new Flume servers. So basically, one single server can do 14 megabytes per second, 1.2 terabytes per day. It's about 70,000 events per second, assuming that the event is 200 bytes each. The storage tier is very similar. So the events come from the collector tier that are in multiple data centers, and it's basically the same scaling strategy. You scale by adding Flume servers. You can also potentially scale internally in Flume by adding file channels. If you have a lot of disk, you can add new channels to stream the data. But if you don't have many disks in a Flume server, you have to scale out by adding servers, which is a little bit ineffective. So Solr Cloud is the last step in a scalability pipeline. So this is again the Solr cluster. In this case, there is 6 servers, 3 shards. So the workload that comes into this cluster is indexing workload. There's thousands of indexing requests per second, and not so many search queries. So we don't have to worry about the search query rate because it's very low compared to the indexing rate. The rule of thumb here is that indexing can be done about the rate 1,000 transactions per second per core, which translates into 16,000 transactions per second per server if you have 2 times 8 cores in a server. And like in this example scenario, there is 3 shards, so it's 3 times 16, it's 48,000 transactions per second. So it's pretty good rate. So, okay, recap about syslog pipeline. So in this example, we have a syslog coming from central syslog servers. It's forwarded to Solr using Flume, and specifically with Flume offline Solr sync, which makes it much easier to parse the events. to Solr Cloud, and then the client is done with Hue Solr Search UI. I got some examples of that. All right, screenshots. So here's a screenshot of simple search. So the key here is that you have to have a way to search by time. Like every search is limited by time. So like you can have a last 15 minutes, last hour, last day, and so on. So whatever you do is limited by time range. And you can sort fields by specific fields that in the schema. And you can facet by the schemas, like here's simple faceting by host name, by error type, and by Cisco product. So you can click through this to pretty easily see what's going on without even typing any search queries at this time. So this is really nothing new. Like this is implemented with many other systems as well. And here's another sample that you're searching something in a specific field like IP address, and you got wildcard query highlighting. So this is the standard Solr. There's nothing new here. So summary. So we got data coming out of various sources, like mainly from local files that are parsed by Cloudera removlines, indexed with Solr Cloud, embedded in CDAs. This is the Cloudera search implementation. And you can also do batch indexing using MapReduce, using the same templates. So now back to the original quest that you want to know when things are going to break. So since you got the data in HDFS, you can use your favorite tool like Tableau or any, like if you're a data scientist, you can do the data mining and do your predictive analytics. For example, like Cisco already does that for the Cisco proper. Like Cisco devices send these problem reports back to the Hadoop, and that data is mined, and there's some predictive analytics to predict that which servers are going to fail soon. So they actually go and replace servers before they failed already. But so that's kind of, we haven't done any of that work yet, but that's a possibility once you got the index and the detailed data in the same place. So that's all the material I have. So if you have any questions, got time for that. So right now we are just starting up. So it's sized for 1 terabyte per day, but we are only getting like less than 100 gigs right now. Right. So the reason is that you can have detailed data as well. So with Logstash you have the index data. So once you sorry, asking about repeat the question. So the question was why not Logstash? Like why bother doing this thing? And the answer is that Logstash is a great tool, and it does actually. The removlines are reusing some of the Logstash work, but what you miss is the detailed data and Hadoop analytics. So if you can solve your problem with search, you're good to go. But if you want to expand from there, then it's good to have the detailed data. Oh, that's a question.
2 questions. Did you use the Solr grammar for your searching, or do you try to abstract that? And the second question is did you tweak any of the relevance or the ranking for your results?
No, we are not that far yet. So we're just getting the data in. So that's the next step to make the search much more relevant.
So who's the main user then?
For this use case, it's the operations. So it's for cloud services to find when things break, and basically it's your Splunk use case. If there's no other questions, thank you very much. Thanks for staying late Thursday, and have a nice rest of the conference. Thank you.